In this video, I'll talk a little bit about visualizing the eigenvalues or poles, as they're called, of second order or higher order systems. And we'll talk about why this is important and how this can be used for design, this visualization. So let's continue from where we left off at the end of the class on Tuesday, which is these eigenvalues for the aircraft dynamical model. So this was the aircraft longitudinal model that I gave you in the exam, and it was a fourth order system. So the aircraft longitudinal model from exam 6. It's a fourth order model which decomposes into two second order modes. So here is one pair of eigenvalues, complex conjugates, and here is the other. So let me color code them so I can draw them accordingly. Now I can draw them on what's called the Argand diagram, which is the real axis versus imaginary axis. Okay, real part versus imaginary part, and we draw the poles or the locations of these poles accordingly. So if you have taken some sort of calc course where they talked about the Argand diagram, this is what it is. Okay, now let's look at the red one first. It has a real part of negative 3.37. So let's say this is roughly negative 0.37, and I'm quickly going to run out of room. So let's say this is negative 0.37. And not to scale, but let's say this is plus or minus imaginary 0.887. So this is plus 887 minus 887. So the eigenvalues are here, the red ones. There's one over here and there's one over here. Okay, so that's one pair. And on this diagram, the blue one will actually be very, very close over here. So as you can see, the real part of this pair of eigenvalues, of the blue pair, is very small. It's 10 to the minus 3. So it's 3 orders of magnitude smaller than this one. So very close to the zero real line, right? So this line, this vertical line, is where the real part switches over from negative to positive. So it's very close to that, still on the negative side though. And the imaginary part is still, it is a little bit larger than the real part, but still very small compared to this one. Again, this is 0.887, this is 0.067. So 10 times or more lower. So this is what it might look like. Okay, and this is actually pretty prototypical of aircraft longitudinal dynamics. Now, the one thing we should note from this visualization is that it immediately tells you whether the system is stable or not. So if all of the eigenvalues are on the left-hand side of this imaginary line, then the system is stable, because that means that all the eigenvalues have negative real parts. So this part over here is where the system becomes unstable. So you shouldn't have any eigenvalues here. And the reason, of course, is that if you're here, what it means is that the real part is positive. So per our original observation that the eigenvalues need to have negative real parts, this would be the unstable region. So that's what we need to ensure stability. But this visualization can actually tell us more. It can tell us something about the characteristics of the transient response as well. So other than just the stability, it can also tell us what the transient response looks like for the typical the second order modes and the first order modes, and that's what we'll see on the next slide. This is the standard second order form. Hopefully this is very familiar to by now. So the transfer function, or maybe a term in the partial fraction expansion of a transfer function, either one, looks something like this: omega n squared over s squared plus zeta omega n 2 zeta omega n times s plus omega n squared. That's the standard form. And we have seen by now plenty of times that the eigenvalues corresponding to this transfer function are this complex conjugate pair, minus zeta omega n plus or minus I multiplied by omega n multiplied by under root 1 minus zeta squared. And these eigenvalues are the exact same as the roots of this denominator denominator polynomial. Okay, so that we have seen plenty of times. Now let us try and draw these eigenvalues over here on the same type of plot, real versus imaginary. And let me try and draw this without using numbers. So what I'm trying to draw here is something that looks like this. The eigenvalues will be somewhere over here, and I'm assuming omega n squared is positive, of course. So these will be equally spaced or symmetric about the real axis. So this distance is the same as this distance. That's because they are complex conjugates. So what this means is, in this picture, this distance over here is the real part, which is zeta omega n. Okay, so this distance is zeta omega n, so this number over here would be minus zeta omega n. So we are on the negative side of the real line, well, stable, so that's why this will be negative zeta omega n. Similarly, this distance over here is the imaginary part, which is equal to omega n multiplied by under root of, let me draw it on the other side because I need this. So this distance over here is omega n multiplied by 1 minus zeta squared. That is the distance, and that is the same as here. So these are symmetric. Okay, so at least we know how to locate these eigenvalues. Now let's note a couple of things about them. Let's note first of all that if I square the real and imaginary parts and add them, I get omega n squared. So if I square them and add them up, right, I get omega n squared. But remember from your complex numbers basics class that this guy is nothing more than the magnitude of the complex number, which means that if I wanted to plot this whole thing on the diagram over here, this is nothing more than the distance from the origin. Okay, so this is my origin over here. This distance is omega n squared. This distance along the or a straight line from either of these eigenvalues to the origin is omega n, not omega n squared, same as this distance. So this is omega n. Okay, that is omega n. And immediately you'll realize that this angle over here, this angle, which is the same as this angle, is dependent only on zeta, right? It is not dependent on the natural frequency omega n. It is only dependent on zeta. So this is a good time for a quick refresher of what these symbols mean. Remember, omega n was the natural frequency, and zeta was the damping ratio. Zeta was the damping ratio. Okay, so that's what this means, and you'll find that this angle over here, this angle is, if I call that beta, that beta angle is given by the tangent inverse of 1 minus zeta squared over zeta, right? The omega n cancels out. The omega n cancels out. So this angle only depends on zeta. It does not depend on omega n, the damping ratio. Okay, so just by looking at these eigenvalues, now what we should try and do is try and get some intuition about how the system behaves just by looking at this diagram of the eigenvalues. Okay, but even before you start doing any calculations and such, you should try and make some qualitative conclusions about what the system is doing in terms of its transient response. The steady state response, we can't really find out anything other than stability. So if they are all on the left hand side of this imaginary line, it's stable, otherwise not. But the transient response, we know by now how to relate the transient response to zeta and omega n. Okay, so at least zeta. So that's what we need to develop more of an intuition for. So let's try and do that. Let's try and get some intuition about this. Now again, let's plot this, and now instead of plotting with any numbers, let's just suppose the eigenvalues were here and here. And now I have listed the expressions that we earlier saw for the settling time and the peak overshoot, and try to make sense of what it means, or what these eigenvalues mean in terms of the settling time and peak overshoot. Here is one thought. Here's one thought. 4 divided by zeta omega n is the settling time, which means that the larger the value of zeta omega n, smaller is the settling time. Correct? So the larger this denominator, smaller will be the settling time. But zeta omega n is whatever it is along this real line. So what it means is, the further along you are into the left hand side of this diagram, right, the settling time decreases. So smaller settling time this way is one of the conclusions, because remember I said in the previous plot that this was zeta omega n. So smaller settling time this way. Similarly, we saw that for the peak overshoot, higher the damping, lower is the peak overshoot, right? So the peak overshoot versus damping curve, which we drew in class, went something like this, correct? So this was peak overshoot versus zeta. So we saw that for zeta equals 1, you don't have any peak overshoot, whereas for zeta equals 0, you have peak overshoot equals 1, as in it overshoots by 100%. So all we have to do now is identify where are the areas where zeta is big or small, and that we can identify from the previous slide, which is basically saying that locus or the locations where you have constant zetas are straight lines from the origin. So let me try and draw this line that connects this eigenvalue to the origin, this angle, larger this angle, larger is, or rather smaller is the damping. So larger this angle, smaller is the damping, which means larger is the overshoot. So this means larger overshoot. Okay, so in the extreme case where you have zero damping, okay, smaller damping goes up this way. In the extreme case, if your eigenvalues were actually here, okay, suppose your eigenvalues were here, these distances being equal, so now you have zero damping, okay, zero damping, which means this line, this black line went from here to here, okay. So you have a large overshoot. In fact, that overshoot is 1. It's 100%, because now you have eigenvalues on the imaginary axis, which means you're going to have constant oscillations. Okay, so that's one thing you should notice, that if it's on the imaginary axis, then the system is not stable. So your response is going to be of oscillatory kind with no decay. If the eigenvalues are on this side, then it's actually unstable, so you'll have divergence of some kind. But here you have steady, constant oscillations, and that's the case where you have zero damping. But if you're closer to over here, so if this angle is small, then you have also a small overshoot. So that's another piece of information that you can get from this diagram. So now on the next slide, I'm going to draw this diagram with a grid that is different from the usual grid, and then we'll try and make sense of it. So here is the grid that I do, quote unquote grid. So it has, or it's more like a polar plot if you're familiar with that. So I have these circles, well, trust me, they're circles, and then I have these straight lines that all go back to the origin over here. And these are contours of constant natural frequency and constant zeta respectively. So each of these is a locus. So this circle, semicircle rather, is a locus of constant omega n. Let's say omega n equals I don't know, 1. Okay, then this is omega n equals 2. This is omega n equals 3. So each of these semicircles is a locus of constant omega n. Now what is omega n? Remember, our eigenvalues were minus zeta omega n plus or minus I omega n multiplied by 1 minus zeta squared, corresponds to a transfer function of the kind omega n squared over s squared plus 2 zeta omega n s plus omega n squared. So that natural frequency is, so you'll find that these are locus, this is the locus of constant natural frequency. Similarly, these lines, the red lines, are loci, or each one of them is a locus of constant zeta. So let's say this one over here is zeta equals to I don't know, 0.8. This one is, let's say, zeta equals 0.6. So decreasing as we go upwards this way, right? And this special line, this line would be zeta equals to 0. Okay, this line would be zeta equals to 0. And these are symmetric on both sides, on the top and bottom half of the real line. So zeta keeps decreasing as we go along, and it doesn't decrease linearly, so it has a tangent inverse relationship, so you'll have to plot it. But anyways, you can figure out the actual numbers later on, and it's very easy to do. But this would be, for example, zeta equals 0.4 or something like that. So you can impose this grid on this visualization and immediately find out, right? So if somebody gave you an engineering paper with this grid instead of the usual Cartesian grid, and then if you plotted, let's say, the eigenvalues of the system and said, okay, these are here and here, you would immediately find out that the natural frequency is, let's say, something like 2.5, and the damping is something like maybe 0.5 or something, right? So you could locate the parameters, zeta and omega and parameters, immediately just by looking at the picture if this grid was superimposed. The other thing you can do is use this diagram for design. So you can say that you want your desired eigenvalues. So that's actually the most useful part of this visualization, is that these curves, right, or rather these eigenvalues, these can be your desired eigenvalues. So that's what you're trying to achieve, and that's where this becomes a little useful. And you'll see that there are tools that allow you to tune the gains of a PID or a P controller such that you can achieve these desired locations. So let's look at a very simple example. So here's the example. This is what we looked at when we talked about the differential drive model. The open loop, or the actual plant model, was this 5 over s squared. We talked about this, and the first thing we tried was to plug in a proportional controller to see if it works. So now let's put this on the visualization and see what happens. Okay, so the open loop or the original plant, which was this guy, has two eigenvalues which are both 0. So what I can do is I can put two crosses, one on top of each other, right here at 0. So those are the eigenvalues, and that's it. That's the visualization. But now the closed loop transfer function looks like this. Closed loop transfer function, we figured this out in class at some point, looks something like this. And the denominator has roots at plus or minus I under root 5 kp. Okay, so that's easy to see because kp is positive. So it has two imaginary roots. So what it means is, let's say I plugged in kp equals 5. So that means the roots of this thing will be plus or minus 5. So if I plug in kp equals 5, I get two roots over here. So let me draw them in a different color. So this guy over here, plus or minus 5. And you can see immediately that for different values of kp, I'm going to get different roots all along this line, right? So I could say that these two roots travel along this line depending on the value of kp. So roots depending on the value of kp. Right? So that's something that's fairly obvious. But now if somebody told you a little bit more information, let's say somebody told you that there was this magical control. Now let me get rid of this kp, and let's pretend that we had a different controller on the next slide. So let's say there was a different controller of some magical kind, which also had some parameter, let's say k, okay, to be tuned, some parameter to be tuned, which we want to find out. And let's say somebody magically told you that as you increase this parameter k, these eigenvalues actually go this way. Okay, these eigenvalues actually go this way with increasing k. suppose somebody told you this. Suppose somebody gave you a visualization that said, as you increase k, the eigenvalues of the closed loop transfer function go along this red line. So two complex conjugates. So let's say for a certain value of k, they end up here. Then you could actually use this for design, right? Because if you say, hey, I need my desired eigenvalues, let's say here and here. Let's say these are the desired eigenvalues. Then from this plot, you could pick the value of k that gives you those desired eigenvalues. Okay, or at least maybe your desired eigenvalues were here. You could at least get close. You could at least get as close as possible. So this could help you figure out the parameter k that would give you the desired eigenvalues or something close. So that would be a good design feature, and this is actually used quite commonly in control design. So this kind of a plot is called a root locus. Okay, MATLAB can plot it very easily, and I'm not going to spend too much time talking about how to plot that and so on, but it's a very useful tool to design or tune certain parameters if you know where your desired eigenvalues are. So that's one benefit of this visualization. So the obvious question is, okay, so how do I visualize where my desired eigenvalues are based on the requirements? And that's something we saw before. So if you have a settling time, given to you, then you're looking for eigenvalues that are to the left of a certain line. So this is the let's say your requirement says settling time no more than 5 seconds or something, right? Then this guy is zeta omega n, right? So this guy 4 over zeta omega n is the settling time. So this guy should be 0.8, right? This distance should be 0.8, and you don't want your eigenvalues to be anywhere to the right of this. So you want your eigenvalues to be somewhere here. Only those eigenvalues will satisfy the settling time of 5. Similarly, if somebody told you that the peak overshoot, let's say the required peak overshoot was some number. Let's say the required MP was, let's say 10%, which would give you a required zeta, right? Required zeta, it works out to around 0.83 or something like that. Okay, that means that you would try and plot a couple of straight lines that correspond to zeta equals 0.83, like I said before. And again, MATLAB can do this for you automatically, so you don't have to worry about how to plot this. So if you could try and plot two straight lines that correspond to zeta equals 0.83, you don't want your eigenvalues to be outside of that cone anymore. So you want your desired eigenvalues to be only in this region, okay, only in this region over here. So then you could just visualize and say, okay, pick eigenvalues that lie here, and then try and design a controller that puts those closed loop eigenvalues over there. So that's how you would use this visualization tool. And in MATLAB, I'm not going to make you use it too much, but look up the command pzmap, and that'll help you visualize this these kind of plots for the homework problems that you have, just to gain a better intuition into these kind of things.